video of this part, B.4, examples of asymptotic notations. In this part, I will give you several examples. When we start, let's look at a very simple example. The first one, show that n plus 2 is contained in big theta of n. All right, yep. First, we know the meaning of big theta. And here, we need to do both upper bound and lower bound. Okay, yeah. N plus 2 here, but C1 multiple of n, upper bound, C2 multiple here, lower bound. It's easy, so we can find those two constants easily. So let's do it. First, we start with n plus 2. For the lower bound, can we find some constant multiple of n that is smaller or equal to n plus 2? As simple as possible. Yes, just n. And strictly less than n plus 2, right? And we also should give the range when this inequality is true. Because we only consider non-negative n, so we put n greater or equal to 0. When we consider the problem size, we never consider negative size, right? N cannot never be negative numbers. Yeah. So that's the reason we just write n greater or equal to 0. Yeah. C2 equals 1 times n. The other side, the upper bound part, because we want to have a multiple of n. So when we compare with the original formula, the first term we keep the same. The second term 2, we want to replace the second term by a constant multiple, and we feel the simplest one is just the n. If this expression is greater than that expression, the range of n should be given, greater or equal to 2. That range should be given. Okay? Otherwise, if n less than 2, then it is not true. This one not true. Okay? So that's why we should specify the range that it is true. All right? Yeah. So then we have the upper bound. Another multiple of n, C1 equals 2. So we get both C2, C1, and N0. Remember, we need the N0. N0. Both inequalities should hold, so we pick this one. When this is true, then it implies that one also true. Not the other way around, right? So we N0, so this is N0 equals 2. Yeah. That's our first example. Our second example show that n cubed belongs to big omega of n squared. Big omega. So this time, we need to work on big omega case. Big omega case. Yeah. That means we only need to find one constant, greater or equal to c of n squared. Right? Yes. Some constant c, right? Yeah. But we know, we just choose constant c equals 1 here. N cubed greater or equal to n squared for what range of n? For what range of n? We can see for all n greater or equal to 0, including 0, it is true. Yeah. So we choose c equals 1 and 0 equals 0. you can see we try to match its definition, the definition of that big omega notation. We try to fit it. Yeah. Here, easy. Yeah. 2 simple examples. The third one, a little harder than the first 2. Still, big theta, you need a lower bound, upper bound. Okay, yeah. But try to use the simplest possible C1, C2. Okay, yeah. All right. So let's do the work for the lower bound. Easy. We just remove 2. It is greater than n cubed. Yeah, greater than n cubed. Yeah. For what range n greater or equal to 0. Yeah. So lower bound is very easy. Now the upper bound. The upper bound. Okay, yeah. Still, we replace 2 by n, and we want to get a larger after the replacement. We want to get a larger, the value. So we need range n greater equal to 2. Yeah. So we get constant multiple to n. But remember, we need to take cube. Okay? So we get a times n cubed. A times n cubed. So constant C1a, C21, n0, 2. Yeah, so we get those 3 important numbers, C1, C2, n0. So we solve the problem. Okay? We solve the problem in this way. Yeah. Okay, all right. The next question. Show that log of n belongs to little o of n. When you see little o, you have to take the limit. Don't use upper bound, lower bound. It won't work. You have to take the limit. Okay? Yeah. So let's take the limit. But here, n is a discrete variable. Discrete. It only takes the discrete values. 1, 2, 3. Not 0. You cannot use 0, right? Yeah. Log of 0, it is not defined. Okay? So you cannot take 0. So 1, 2, 3, all the positive integers for n. Yeah. We are aware of this n is a discrete variable, so we cannot take derivative. The reason I mention this, if you want to use the L'Hopital's rule by taking derivatives, you should be careful. Okay, yeah, so here we replace n by a continuous variable x. This, we assume x changes continuously in all positive real numbers. Positive, yeah. All right. So when we use a continuous variable, we can take derivative. Yeah. So L'Hopital's rule. Now, let's check if we can apply L'Hopital's rule here. Yeah. Because this ratio is a infinity over infinity indeterminate form. Infinity over infinity indeterminate form. So it is okay, we can take L'Hopital's rule. Now, all right? And remember, the base, we use some a greater than 1. Yeah, we assume that. Yeah. So then, when you take the derivative, the numerator just the 1, the denominator just the 1, the numerator, you need to know that formula. Okay, derivative of log base a of x. Okay, 1 over natural log of a times x. Natural log of a. Okay, yeah. Then, after simplification, you have this expression, but this part constant. When n goes to infinity, you have a constant times 1 over x. That is 0. 1 over x. The limit is 0. So the whole limit is 0. If the limit is 0, then we can go back to, I need to write one more thing. Then this, because here we use the continuous variable, now we can take special values for the continuous variable to get discrete variable log n over n equals 0. Right? Special values. Yeah. After we have that, then we can say log of n belongs to little o of n. So we complete. Yeah. So we complete the solution. Yeah. All right. So next one. Number 5. All right. This time, the power function, n to the dth power. D is a positive constant. N to the dth power belongs to little o of an exponential function a to the nth power. Yeah. And d greater or equal to 1, a greater than 1. And we also want d as an integer for this example, as an integer, because we want to make it a little easier. But later, we can remove that restriction. Later, d is any positive number, positive real number, then we have the same result. We can use that later. But for this example, I like to use the integer, positive integer d, so our solution could be a little easier to get. Yeah. All right, so let's look at the solution. We try to use the L'Hopital's rule. When we use the L'Hopital's rule, we change the variable to continuous variable x. And we also notice that this is an infinity over infinity indeterminate form. So we can use the L'Hopital's rule. Take derivative. Derivative of the numerator first. Numerator, we use the derivative power rule. Derivative has a power rule. Okay? Yeah. So this is the formula from the power rule. D times x to the d minus 1 power. That's what we call the power rule. Okay? Then, derivative of exponential function a to the x, natural log of a times that same function, a to the x. Yeah. All right, so that's the first time we use the L'Hopital's rule. After that, if d greater than 1, that means it is still an infinity over infinity indeterminate form. So we can apply another time L'Hopital's rule. Take another derivative. Okay, yeah. So here we take another derivative. Yeah, so, all right, yeah. Hope you can see it. D times d minus 1, yeah, because I want to leave that power rule there. All right, let me just remove. I put the power rule here. Because I know that some students do not know this power rule. At least I tell you the name, you can search the web and get a power rule, right? You know what to search. Yeah. All right. Then, that's the second time we use the L'Hopital's rule, and so on. So If d greater than 2, we can keep doing this until we get d minus d. Yeah. So finally, we will get to a point, d minus d, because d is an integer. D is an integer. Eventually, d, every time it is reduced by 1, by 2, by 3, by 4, and finally by d, d minus d. D minus d, it is gone, right? So this whole thing, x to the 0 equals 1. We know that. X to the 0. X is a positive number. Positive number to the 0th power equals 1. So it's gone. Numerator, the variable x part is gone. All right, so we can simplify as this one. D factorial over natural log of a to the dth power times a to the x. This time, it is not an indeterminate form, okay? Yeah. Because the numerator is a positive number, fixed number. It is not an indeterminate form. Infinity over infinity, 0 over 0. It is not an indeterminate form. So we cannot use L'Hopital's rule another time. If you use, it's wrong. You get a wrong answer because it's not an indeterminate form. Okay? All right, so, but we are ready to get an answer because the denominator goes to infinity. Numerator is just a constant. Constant over infinity, it's 0. Okay? If it is 0, then, yeah, so before we make conclusion, we can go back to discrete version, replace x by n, also equal to 0. Because we just take special values for x. For continuous variable, it's true. For selected discrete values, also true. Okay, also true. When we look at the limit, it's also true. Okay, yeah. So with that, then by the definition, we get that little o conclusion. Okay, yeah. So we complete this example. Example number 5. All right. Next one. Example number 6. This one. Log base 2 of n belongs to little of root of n, square root of n. L'Hopital's rule again, yeah. Use the continuous variable, L'Hopital's rule, take derivative, okay, yeah. And we write x to the 1/2 power. In order to apply the power rule, power rule also works for non-integer value. It also works non-integer value. Yeah, so we can apply the power rule. Then we plug in, use two formulas, so we get this one. After simplification, we get this. Now this ratio is not an indeterminate form. It's not. So you cannot apply L'Hopital's rule another time. Yeah, you have to stop. Yeah. But at this point, we are ready to get the limit value because the limit goes to infinity, 2 over infinity, right? Yeah, so you think about it, 0. So if it is 0, then we can go back to the discrete version. Discrete version. Also true, right? It's also true, then we have the conclusion. All right. Yeah. Next example, number 7. Yeah. Show that natural log of n belongs to little of n to the dth power. So what is that d? We only require d greater than 0. If d greater than 0, then natural log of n has smaller order of growth than n to the dth power function. Even that d could be very small. You can imagine d could be that 0, 0, 0, 0, 0, 0, 1, because it is still positive, right? Even d is this small, natural log of n still cannot compete in growth with this function. Still cannot grow as fast as this function. This part a little hard to understand, but you need to. After this example, you need to see that. We prove it. We prove still L'Hopital's rule. Use the continuous variable. It is an indeterminate form, infinity over infinity indeterminate form. So we can take the limit 1 over x numerator, denominator power rule. Okay? Yeah, power rule. Yeah. Then after simplification, we get this expression. And this one, it is not indeterminate form. We cannot use L'Hopital's rule another time, but we are ready to get its limit. 1 over infinity, x to the d, that's infinity. Even d could be a very small number, but still goes to infinity. 1 over that infinity, 0. Yeah. So in that case, we can write, after that, we can write back to the discrete version, also 0. So we can get that conclusion after that. Okay? All right. So you can see we use the same way in all several. Yeah, these 3 questions, we use the same method, same way. L'Hopital's rule, I repeat 3 times. Yeah. So try to get those important steps. Yeah. All right. The last question of this video, number 8. This one is hard. This one is very hard. Show that n factorial belongs to little of n to the nth power. Little o, n factorial. The hard part is how to estimate n factorial. So that's very hard. N factorial. How to measure it? Yeah. We have to use a special formula to estimate n factorial. That formula called Stirling's formula. In calculus, in Calc 2, you can learn the Stirling formula. Or you just search the web. You can find the Stirling formula. Here, I give it to you. The first version, n factorial approximately equal to this expression. That's the first version. But this version is not very convenient. We have this approximately, but what do you mean exactly this approximately equal? Right? Still not very convenient. So this version, not very convenient for our calculation. Yeah. So for that reason, we want to get a more convenient version. So this is the convenient version. Yeah. So we estimate n factorial using 2 functions, One for lower bound, another for upper bound. Lower bound, upper bound, right? Because for our asymptotic notations, we need lower bound, upper bound, right? For you, yeah. Yes. And here, yeah, although little o, yeah. But our asymptotic notation, we need a lower bound, upper bound. Okay, sometimes, yeah. So better than that approximately equal. Approximately equal, we don't know when we compare which one is larger, which one is small. We don't have that information. Yeah. All right. Yeah, because for this video, we already we run out of time. In order to complete this example, I put the remaining, the solution part, in our next part C of Module 2. Now, the first video of Part C, I will complete the solution of this example. All right, so let me finish this last